Let's take a closer look at the aldol condensation product. We've already seen that aldehydes and ketones plus NaOH can do a self-condensation, and I hope that you don't have any trouble coming up with that product now. And of course we make some water. We're not going to worry about that much right now. We could draw some resonance of this compound though, so let's go ahead and do that. And of course the carbonyl can push electrons onto the oxygen. That gives us this separation of charge, and then we could also draw a allylic cation resonance pattern like this, which gives us a new cation position, and those are the three resonance structures of our aldol condensation product. And so this helps us decide that, or it helps us show that aldehydes are electrophilic at this carbon because we can put a partial positive charge there in our resonance hybrid. But the interesting thing about this alpha-beta unsaturated aldehyde is that it is also electrophilic at the beta carbon. So what we have here is an alpha-beta unsaturated aldehyde, and that of course can be created via an aldol condensation, and it is electrophilic at the carbonyl C and the beta carbon. So let's look at the potential products that we could get. We've seen Grignard addition to carbonyl carbons, followed up with water. Grignard reagents will add to the carbonyl. And we call this 1,2 addition because we're basically attacking the carbonyl carbon, pushing electrons onto the O, and eventually protonating those electrons. So the action happens on these two atoms that are in a 1,2 relationship. Let's use the same aldehyde, but now we're going to react it with what we call a cuprate reagent. Let me try to write it correctly. It should be 2 ethyls, a copper, and a lithium. So this is called a cuprate, and it is also followed by water. And it delivers ethyl anions just like the Grignard did in the previous example. And so let's look at what the product would be here. Here we're not going to affect the carbonyl. We're going to add our ethyl anion to the beta position. So now we have a way to make new carbon-carbon bonds at the beta position. And of course we made new carbon-carbon bonds at the alpha position up here at the beginning with our aldol condensation. So now we have different ways, different techniques that allow us to put new carbon groups at either the alpha or the beta position, depending on if we have an alpha-beta unsaturated carbonyl. And so this is called 1,4 addition. Sorry, I wanted blue here. This is also called conjugate addition. And we've added to the beta carbon. So these cuprates can be created from just about any alkyl halide. Just like we can make Grignards from just about any alkyl bromide, cuprates can be made from any alkyl lithium species, which pretty much mirror alkyl bromides. So we've seen a range of Grignards already in this class. You can pretty much assume that those, if they can be made into a Grignard, they can be made into a Cuprate reagent, so except that we just use 2 R groups instead of 1 here. So we can use phenyl, methyl, ethyl, propyl, isopropyl, all the common ones we've seen thus far as Grignard reagents. We can also use enolate anions. So enolate anions make good nucleophiles for conjugate addition. So if we start off taking this stabilized enolate, we're going to create a negative charge here. We've seen this before using KOH. The second step might be adding the same alpha-beta unsaturated aldehyde that we've seen on the previous slide. Follow that up with H3O+. This is what we're going to get. Here's our starting material, diketone. We're going to make a new bond to the beta carbon of that aldehyde, and the double bond disappears. So we've made this new bond right here. This is the beta carbon of the aldehyde. So we've used this as a nucleophile, and this is called a Michael reaction. Named after the scientist who developed it. And the Michael reaction uses a stabilized enolate. What does that mean? Well, typically it's a beta dicarbonyl compound. There's a table of useful stabilized enolates in your book chapter. But this is an example of one. We could have a diester, we could have a ketoester, basically anything that has two carbonyls or two electron withdrawing groups that can, via resonance, stabilize a negative charge right here. And then a good Michael acceptor, we call this a Michael acceptor. Is the unsaturated carbonyl species, and we can basically use almost any unsaturated carbonyl species. It could be an aldehyde, it could be a ketone, it could be an ester. I would like to point out one. You can see most of them in the table in your text, but one that we've not really considered up until now is a nitro compound on an alkene. And you can see how via resonance we can show that the end carbon of that alkene is positively charged. So we can actually use a sort of a vinyl nitro species. So what happens if we want to use a less stabilized enolate? What if our goal is to take this molecule, deprotonate it, and add it to, say, the same unsaturated aldehyde that we've been looking at? Oftentimes, forming the negative charge there can certainly be arranged, but it creates a less stabilized enolate, and it can be tricky. So we need to find a different way to do this. So the first way we were proposing was LDA followed by the Michael acceptor followed by mild acid workup. But this enolate that I've shown is not well stabilized, right? It doesn't have both carbonyls present. So this just doesn't work as well. Let's look at another option. What if we turn the ketone or the aldehyde into an enamine? And we learned how to do that in a previous chapter. We know that the product here is the enamine, and we also know that it has a resonance structure that looks like this. Which means it is nucleophilic at this carbon, much like an enolate. So it's easier to make enamines. They are more stable because they're not negatively charged, so they're not looking for basically any proton anywhere to do a proton transfer reaction with, and they are still nucleophilic at this position. So you can use enamines as nucleophiles and add them to a Michael acceptor. Let's look at an example of that. So let's say I took my acetone, I created the enolate like you see here. Here's the alpha-beta unsaturated aldehyde. And I can mix these together, and essentially by drawing the first two arrows of the resonance structure of my enamine, I can start a 4-arrow mechanism, 4-arrow push, which gets me to this structure. And as I've been saying in class, it is easy to lose track of carbons here, so let's try not to do that. I'll number 7 carbons like that. And my first 3 carbons are right here. I know that the 3rd carbon made a bond to the 5th carbon, 6, 7, and that's where my negative oxygen will be. So I know I made a bond from 3 to 5. And if you're following along, you'll see that I'm missing carbon 4, and that is still attached to 5. It is still a methyl group, so I'll put it right there, and I will label it. And then I also need to show the CN double bond at carbon number 2, and the quaternary, or at least the nitrogen cation, because I've formed 4 bonds to that nitrogen. And this is then, there we are. This would then be the intermediate, and I can react that with mild acid to end up with this product. And you can see that the mild acid has hydrolyzed the enamine, just like we learned about in the aldehyde and ketone chapter. So we can hydrolyze the enamine by adding water and acid, cleaving that CN double bond, reforming the carbonyl that used to be there up here before we made the enamine. And of course, this enolate gets protonated and tautomerizes to the aldehyde under these mild acid conditions. So 2 things are happening here. The enamine, or in this case the iminium cation, is being hydrolyzed back to the ketone, and the enolate is being protonated to form the aldehyde. So the end result is that I've made this bond right here, just like I wanted to up at the top reaction. And I know some of you were saying, what the heck happened to the original ketone? There it is, sorry about that. But you can see that this product here is the same as this one now that I've fixed it, except that this enolate does not participate in Michael reactions very well because it is just less stable than the stabilized enolates we saw on the previous slide, or it's less stable than this neutral enamine. So if you want to perform a Michael addition using essentially a ketone or carbonyl species that only has 1 ketone, first form the enamine from that ketone or aldehyde, then mix it with your Michael acceptor to make your new bond. This does have a name. It was named after Stork, who discovered the reaction and studied it. So it's called the Stork enamine synthesis. So another thing I'd like to point out is that these are different numbers here. So actually let me use purple so that you recognize that they are different. I'm going to use green actually. Different numbering scheme. All I want to point out here is that we've made a 1,5-dicarbonyl species. That is the product of a Michael addition. So if you ever see as your synthetic target in a synthesis problem a 1,5-dicarbonyl species, you should be thinking about the possibility of doing some sort of Michael addition, and most likely, unless you can tell that the nucleophilic carbonyl portion is very stabilized. In this case, it is not. The nucleophilic portion comes from carbons 1 and 2. We know that because, well, it has to come from one of these two. Neither of them have 2 carbonyls attached to them. So either one is going to be relatively unstable. And so that means that you should be thinking about the Stork enamine synthesis if you are faced with synthesizing a 1,5-dicarbonyl species. Let's take a look at a few examples on the next slide.